untitled gerrymandering. So his expertise is to test dynamic systems. The code that will prepare for him in the future or in the other direction he has been working on for a long time. But today is new topic. Please.
All right, thanks. Thank you all for coming all the way over here, I guess, from the other room. It's nice to be here. It's nice to see you and see old friends in the audience. So, yeah, like Faye said, this is something that I started maybe in 2013. In 2013, actually. And for a while, no one cared, and then all of a sudden, a lot of people cared. So what I'm going to try to explain is a little bit, but I give a more public version of this sometimes where I talk a lot about the politics. To be honest, I'm going to talk more about the math today, but I'm going to spend about 20 minutes talking about kind of the implications and how we use this. So let me start off. So this is joint work with myself, Greg Hirschlag, and a group of a whole bunch of people that you'll get to meet. All right, so we talk a lot about gerrymandering. You know, this is what I found one night while falling asleep in a few minutes at the computer keyboard. You know, various quotes from the news media. But, you know, I guess I should ask you, what is gerrymandering really, right? What is it? And I think a lot of people think they know what it is. And I think if you think about it for a while, you may discover you don't know what you thought you knew. So one definition that people often use is funny-looking districts. Right? This is a funny-looking district. But the problem is that this map and this map are politically equivalent. They lead to the same election results, and this one looks beautiful, and this one looks tortured. All right? So it's kind of like murder, right? You know, if you see somebody who had their head cut off, you might suspect that they were murdered, but not everyone who's murdered had their head cut off, right? So you know, it can tell you what's going on, but it's really not what you should be looking for. The other thing that people talk about when they talk about gerrymandering, by the way, Avanti, if I'm talking too quiet, just let me know, all right? Please, thank you. So, they talk about what they might consider unfair results. And what do they mean by unfair? Well, we'll talk a little more about that in a second. What they often mean is this. They have some idea of what should have happened, and that's usually based on the statewide vote fraction. So here I'm talking about electing people to the House of Representatives, the U.S. House of Representatives. This is North Carolina. This is Maryland. In 2012, 50% plus of people voted for Democrats in North Carolina, and exactly 31% of the seats, or approximately 31% of the seats, went to Democrats. And you might say, that's not fair. And in Maryland, 63% voted for the Democrats, and yet they got 87.5% of the seats. So some other people might say that's not fair. And then they go on and they might say things like, well, you know, given this, the Democrats, there are 13 seats, you can add those up, should have gotten 7 seats clearly. You know, if you know anything about the shape of North Carolina, you saw it a moment ago. It's this long wedge. You know, maybe it just happens. Asheville is out west if you go to the Smoky Mountains ever. And if you start districting from the far western corner of North Carolina, maybe it just happens that Asheville gets submerged in a sea of red and its votes never matter. Maybe that happens. So, you know, there's all these geographic effects that could happen, right? The effects of suburbs, the effects of urban cities. You know, there's lots of things that can happen. And so this idea that all of a sudden you should just convert a statewide fraction doesn't really make much sense. But you hear, oh, shoot, this slide's out of place. We'll come, okay. Well, darn it, this slide's out of place. Anyway, so here's this slide's out of place. What this is actually is to try to just point out that some of this talk is about a bunch of mathematics that was used in a lot of places. So here's a report that Munduchin wrote for Virginia, to the Commonwealth of Virginia. These are 2 court cases. This is Common Cause versus Rucho and Common Cause versus Lewis. Those are 2 different court cases that I was actually an expert witness in. One of those went all the way to the Supreme Court, and both of them have led to right now the North Carolina maps in North Carolina being overturned. And you may have heard the Supreme Court decide not to do anything about it, but it was then brought up in state court, and the state court overturned the maps. And there's no appeal to the Supreme Court because it was against the state constitution, much like what happened in Pennsylvania. Here's another report from Pennsylvania. Here's some amicus briefs that were filed to the Supreme Court by mathematicians about mathematics. So, you know, this is actually getting some traction. So, let me tell you now. Let me go back to my story for a second. So both of these, you know, ideas of what gerrymandering was. Oh, wow. I told them that my screen, no, the screen stopped playing. It just went out. That's weird. I don't know what happened. So the idea of gerrymandering is often this idea that if you look up the dictionary definition, it's that you manipulated or changed the outcome by manipulating the boundaries. And somehow inherent in that definition is the idea that you knew what should have happened. Right? To manipulate, to change the outcome means you knew what was going to happen. And the two slides I gave you before was somehow often based on proportional representation. That was the idea of what people thought was going to happen. And so, you know, what we set as our question was maybe instead of that, we should be thinking, what would have happened if no one had had any political agenda? What if there had been no political agenda, what would have happened? That was the question we posed to ourselves. So people have lots of attempts to do that. So here's some attempts. One is proportional representation. They say, well, I think what should have happened is it should have been proportional splitting of the seats. The problem with that is that's not our system. We can have a conversation about changing the system, but that's not our system. Another thing that people talk about in the press and in political science literature is this idea of partisan symmetry. And partisan symmetry is the idea is if you get 60% and I get 40% and then we switch sides, the reverse should happen. But it's always talked about at this statewide level. It's never talked about, you don't pick up all the people from the suburbs and switch to the actual where they live. So it's really not a symmetric relationship. And so it's flawed, I think, as far as logic goes. And then there's the efficiency gap, which has always been a bad idea, and I don't have a lot of time today, so I won't go into it, but there's a nice case by Moon Duchin and co-authors that talks about that. And whenever these things fail, people often invoke the idea of geography, the political geometry of the state. And what I want to say is, like, let's just go straight to that from the very beginning. Let's talk directly about that. You know, what I want to make really clear is to separate the idea. This, if you don't like that we don't have a proportional representation system, that's fine. You can have a conversation about that. We can change our system. But I'm not having a conversation about changing our system. I'm having a conversation about evaluating the system we have and how it was implemented. So you have to separate those two different concepts of fairness in your head and what you want in two different directions. All right. So let's say you wanted to compare some maps. Here are 3 maps. This is the map that North Carolina has used in 2012. This was deemed a racial gerrymander. And then they replaced it with this map, which was the map we used in 2016, which was just thrown out. And while considering that map, they considered just yesterday or the day before, maybe using this map, which was made by a bipartisan collection of judges in North Carolina as an attempt to show what would happen if a bipartisan collection of non-elected officials tried to draw a map, following a very rule-based approach. So if you want to compare these maps, you might look at them and start trying to contrast them, like, oh, I don't know, Asheville is there and it's not there, and that's something different. You can start that. But it'd be helpful if you had a few more maps, right? And maybe that's not enough maps, so you'd like to have a few more maps, right? So, and then you start getting an idea. So what I'm going to propose is that we're going to have a large collection of maps that are constructed just following some minimal principles that are nonpartisan. And then we're going to use that ensemble of maps to use as a statistical test, to use as a null hypothesis as to what would happen if there had been, no one had their finger on the scale. And then we're going to use that to talk about what happened in a particular map, whether it was typical, whether the structure we see was what we would normally see, or whether it seemed like somebody guided it to an end. Yeah, please interrupt.
Is that in any? Does anybody realistically believe that there isn't a hand on the scale?
I mean, sometimes they say quite explicitly there's a hand on the scale. But you have to show, but they might say things like, in court, they'll say things like, the reason it looks the way it does is because we decide to split less counties than we had split previously, and doing so forces us to have maps that have these properties. And then you have to answer that question. That's not hypothetical. That was said to me on the stand. So I'm going to create an ensemble of maps with no regard to partisan or demographics, partisan information, and I'm going to use this as a baseline to compare things. I'm going to be building a null hypothesis, all right? All right, so this kind of, what I could talk about breaks up into a kind of 3 steps. How do you design this ensemble, this collection of maps? So just to go ahead and tell this audience, I'm going to put a measure, a probability measure on the space of all possible redistrictings of North Carolina, and then I'm going to sample from that measure. And that measure is going to encode my beliefs in what are good maps. Then we can talk about how well do you sample from that collection, that measure, that probability measure. That's a science question, which is what a large chunk of this talk hopefully will be about if I get there. And then there's an interesting conversation about how do you explain it to lawyers and judges and the public. And when I give a more public lecture, I actually talk mainly about this. All right, but lucky you get the map today. So here is an example. So this is actually what was presented in Rucho, which was the case in the Supreme Court. These are the actual plots. So we took our ensemble, in that case, of only 24,000 maps. We ran a historical election. So that means in every precinct we had historical voting data from the 2012 election, the 2016 election. And we recalculated what happened with that particular choice of precincts and districts. We saw who won which districts. And we did that for every one of our 24,000 maps. And then we looked at how many Democrats were elected. For instance, we're going to do more than that eventually. Because I don't think you should just do that. And that was something that was not done well in the Supreme Court oral arguments. I think they fixated too much on just this one number, which is not, I don't think, the right thing to do. And you get some idea. This was a more Republican election. It has less Democrats elected. This is a more Democratic election. This is the one I showed you. And now we can situate those 3 maps I showed you. These 3 maps. So if I situate them, here they are. Here are the maps that North Carolina has been using for the decade. And here's this one that was drawn by this bipartisan collection of judges. You know, one of my goals here is I don't want to just give you a p-value or give you some number and say good, bad, go home, take away, you know, be angry, be sad, be happy. You know, I want to give you some way to look at what happened and let you draw your own conclusions. So I'll let that sit there for a second. Draw your own conclusions. Since usually I have to explain what a bar chart is right now, I'm not going to do that here. But I will show you this. So after many iterations, I end up with this. So this is a way I actually showed in court, not in Rucho, but in a later trial. So I've taken an election that had 42% Democrat statewide vote. And then I slowly shift up precinct by precinct the votes to change the statewide vote fraction. And we're going to watch what happens. This is, right now you might say, this looks great. This is the map from 2016. It looks great. Let's see what happens. Oh, now it's, yeah, so now, so you notice that 50%, we don't have, the Democrats don't have 50% of the seats, so there is some structural bias. But it took till 54% before that enacted arrow even moved. Right, let's, one more time. So it's going to come up, let's see, when does this even start to move? Ah, there we moved one, there we fell there. So so now it finally catches up. So it's not a question about one election or non-election, it's a question about that phenomenon. That's what gerrymandering is.
That's robust, Jerry.
Yeah, well here's robustness. So that was one set of elections with some spatial distribution. Let's look at a whole bunch of elections. I've ordered them from more Republican to more Democrats. You notice that this barely moves over a huge number of elections, even though the purple bar chart solely plots to the right with more Democratic seats. And the judge's map tracks it to some extent. It's not completely surprising because they had a set of rules. There were a couple criteria. And one of the criteria when they drew this map, they said the map should produce 10 Republican seats and 3 Democrats. That was the rule. If they didn't really say, like, depending on how you vote, they just said we don't care how you vote. This is what's going to happen, okay? And they did a pretty good job. All right. This is now the North Carolina General Assembly, which is our state house. The house, it has 120 seats, so I've clipped the thing here. And I have the same kind of plot again with a whole bunch of data. But notice that now it's not so unusual down here. It's pretty typical. But it doesn't start to be unusual in a dramatic way until you get up to the top. Why? Because that's when the Democrats would break the supermajority line and break the majority line. So we call this a firewall effect. We saw the same thing in Wisconsin when we analyzed the Wisconsin legislature. It's actually quite typical when the party who drew the map would have already won control of the chamber, and it only starts to shift as the chamber's power would have shifted. So it's designed to come into effect. And here we have another movie, and since this is you guys, so what I have here is the order statistics of precinct by precinct. I've ordered them from most Republican to most Democrats, and then I've taken each of those marginals, so 120 marginals, and I've put a box and whisker plot. I don't have to explain box and whisker plot. 50% in the middle, median down, outliers, right? Okay. Hash marks at 1% and 99%. All right. And this is the 50% line. So when a box part moves above the 50% line, that district would flip from Republican to Democrat. And when the dot does, that's when the inactive map would flip. So watch what happens. Look up there. It's pretty typical. It's moving along with it. It's not so unusual. It's going to move a little bit. It's going to kind of come along. Those dots are crossing over. But now when we get to this region where there's a depletion of Democrats in those districts, it's going to stick. And that depletion of Democrats is what led to this effect. And by the way, just a spoiler, we see the same thing in Maryland, in the other direction. So it happens on both sides. All right? So now it's sticking. You see now finally it broke here, but already the power would have shifted to the other chamber, and this will stick here for a minute while this slides along. Because again, we're in this area where we have a depletion of Democrats. So let me show you now the whole box plots back to the North Carolina congressional election. Whoops. Here they are again. So this is the judge's map, which kind of tracks the yellow line, which is the median. There's some fluctuation, but the fluctuation is quite typical, and I can make that precise if you want. And then there's this huge jump. And this huge jump, which unfortunately wasn't presented in oral arguments, but it was presented in the court case, it was one of the central discussion points. And what that allows you to do is to talk about these districts are what is called cracked. They've had the Democrats spread out more evenly than they should so that their power is depleted. And these districts are what are called packed. So they've had extra Democrats than one would typically find in them packed. And this effect causes a huge jump between this district's percentage of Democrats and this district's percentage of Democrats. By huge, I mean relative to what one would expect in a neutral plan. And that's what gives this huge insensitivity, this robustness, if you will, the not changing. So you really can see it here. And so I prefer these visualizations so that you understand what's going on. Okay, so I don't have a lot of time, so I'm going to skip this. This is just kind of pulling out the idea that you can actually separate rural versus urban packing and see the effect of that and still understand when there's more effect, right? This is the percentage to get 50% of the chamber in Wisconsin, and you see it often is you only need 46% for the Republicans to get 50% of the seats. So there is a structural advantage in the system, but under the maps that they're using, they need much, much less. So you can suss apart the effect of the system with how the maps were drawn. Also, Roberts, like in his majority opinion in the Supreme Court, he talked about how proportionality was what people were talking about. But proportionality would mean that the blue dots follow this line. They don't. The blue histograms. They're shifted towards this side of the line. There's a systematic tilt to one party. So there's nothing about proportionality here, but nonetheless, there's still this gerrymander. So the whole point is not to have to invoke statewide proportionality. All right, so this is actually Maryland. This same kind of tilt that happened here, you see as you get up here to the Democratic side, this kind of sticks here even though the blue dots move over in different elections. So it's not as dramatic in Maryland because they're going for just the last seat, more or less, that's in play. But there is an effect where they've pretty much decided that one party gets this seat, the other party get all these seats, and that changing opinion and public opinion doesn't lead to flipping a seat, which maybe leads to unresponsive government. Okay. So, how do I encode the math and the policy? So what we do, so here comes the beginnings of the math. It's not quite there yet. So we have it's like an Ising model. We have a 13-color Potts model. So I have all the precincts. There's 3,000 precincts in North Carolina. I have all the precincts in North Carolina laid out and with their adjacency. That's a graph. It's a planar graph, essentially. And from those precincts, I map to N is 13 here. So I label each precinct with a number 1 through 13, and that's what district it's in. And then I create a score function, which is just the exponentiation of some score. It's some probability measure, which is the exponentiation of some score, a Hamiltonian, an energy function, a likelihood, whatever you want to call it, whatever your people call it. And it's made up of a series of terms, which I make to be the sum. And the reason sum is, I think, a reasonable first thing, because at least locally, that means it's product measure. That means I'm not correlating population deviations with compactness deviations, or with, we like to have counties remain whole in North Carolina. It's in our Constitution. We want to satisfy the VRA. Actually, we don't need to satisfy the VRA anymore. That's not because of a change in policy. That's actually because we no longer satisfy the test of states that have to. And the population, for instance, is just the L2 deviation. So I look at the population of each district. I take the population of the state divided by 13, and I know what I want it to be, 1 person, 1 vote. That's the idea that every district should have the same number of people. And I calculate that. And so that gives me an energy, a probability measure which is concentrated on districts which satisfy my design principles better. And it's agnostic to other ones. For the compactness, we calculate the isoparametric constant, right? The perimeter squared over the area, and sum that up over all the districts to give a group isoparametric score. That actually has a name in political science. It's called the Fosbury-Popper score. No offense to the Greeks who maybe thought of it first. Or this Carthage, Dido, right? So there's a bunch of different points of view on this. So I want to kind of insist on one point, which is that I think it's nice to have a known probability measure you're sampling from. There's people who kind of do local optimization or genetic algorithms, or treat this by some other method where they don't know what they're sampling from. And I think that doesn't let you critique it as easily. It's nice to have an actual known measure that you can have a conversation about. And then you can separate that conversation from the conversation about, are you doing a good job sampling it? Okay? All right. So, when should I end? Like, when do we start? After the delay? Or do you want me to stop on time still? I can stop on time. Okay. All right, so like at 20 past? Yeah, 20. All right. So let me talk about generating the ensemble. And that's kind of the main thing I wanted to talk about today. So that last part was the elaborate and long introduction to why you might care about this problem. Because right now we're in the Wild West. It's kind of obvious, like you said. Ones are gerrymanders and ones that aren't. It's kind of pretty obvious. But I think down the road it's going to become much more important that we get the science right. And that's going to happen, and we're going to have to be ready to be able to have this conversation in a more nuanced way. Both from the point of view of sampling and from the point of view of how we explain what we've seen and our tools for understanding the data that comes out of these procedures. All right, so how well do we sample? So I stole this from the IMA website, shamelessly, I forgot to put that there. So I know I probably don't have to do this here, but let me just bring everyone along. Let me explain Metropolis Hastings, all right, sampling. So the idea of Metropolis Hastings is you have some probability distribution you want to sample from, mu, and you have some Markov chain on the state space which doesn't have that as a stationary distribution. And you want to create a new measure that does have that as a stationary distribution. And here's the classical standard Metropolis Hastings recipe. There's lots of variations, but this one is a classic one. So you take a step according to this Markov kernel, from C to C prime, and then you say, did the energy get better? Did my score go down? If my score went down, I say, fantastic, and I step there. If my score went up, you know, if you're trying to sample the valleys of Switzerland, sometimes you have to climb mountains. So with some probability A, I go uphill even though that's not as good. And that probability is this measure, is this number here. Okay? And of course, that comes from the fact that if this measures with this Markov, this system P, which I'll call that transition kernel P, satisfied this detailed balance relationship, then it's a trivial homework exercise in your first Markov chain class to see that mu is an invariant measure for this Markov chain. So if it has a unique invariant measure, if you run it long enough, you'll get samples from that measure. And if you wait between them, they'll be relatively correlated. And what this is really saying is this is the flux. It's the probability of finding yourself in the state C prime, and this is the probability of moving from C to C prime to C. So the probability going in one direction should be equal to the probability going in the other direction. That's called detail balance. So this kind of local detail balance condition is one way to make sure you have a Markov chain that samples from a certain measure. And this Metropolis-Hastings algorithm is exactly designed to enforce that detail balance. Okay? And I won't go into that. Okay, so here's a simple example. This is in fact Iowa. 4 districts. This is the adjacency graph of precincts in Iowa. I see an Iowa. It's in Iowa. In the back. But what we're going to do is we're going to do what every person does the first time they want to sample from something. You do the simplest little spin flip model a la arisen just to get going. And if that works, hallelujah, next problem, move on. So what are we going to do? We're going to look at all the conflicted edges, the edges that go between 2 different colors. We're going to pick them appropriately with the right weight to mean that I'm picking uniformly. So I take into account multiplicity. I'm not going to belabor that point. It's not too important. You can read about the paper. I pick one, and then I push the color across one way or the other with 50-50 chance. Bam, there we go. And then I check the energy of this new state. That's actually what we did for 2 of the core cases. We just did that. All right? So, and just to say on top of this, we use kind of standard, you know, Gell-Mann type convergence testing. So we generated 10 random initial maps using a constructive algorithm. And then we run a Markov chain starting from those 10 different maps. And we have some summary statistics we care about. We calculate the empirical measure of those as we go. And then we compare the total variation distance between each of the chains pairwise across all of them. And then we wait till the soup of that error drops below the threshold. And when it does, we declare victory and we say we can stop running that chain. So when we did that in North Carolina for the congressional district, it doesn't work. It's just, the energetics are horrible. You can't get to it. So we had to resort to simulated annealing. So we heated the system up. We let it mix for a while, we cooled it back down, we let it come to equilibrium hopefully, we checked by doubling the equilibrium run, we picked one sample and then we repeated that whole cycle over and over and over again. In the North Carolina state legislature case, it turns out that you have to redistrict respecting certain groups of counties without crossing their boundaries, which turns this into this product measure over clumps of counties, which means you're solving 20 smaller problems, and we could actually solve that at constant temperature. So in that case, we were actually able to sample at constant temperature. But nonetheless, there's some evidence. So there's this nice paper of Forrest Solomon and company, where they actually look at conductance between different states and prove both numerical, they give some numerical evidence, but they also look at conductances between different states, and they give some counterexamples for slow mixing of the flip state, that it's going to mix slowly. And so there's some reason to think that maybe we need something better. So here's the county cluster. So at various times, I'm going to show you some of these little tiny states. These are actually groups of counties from North Carolina. In the state legislative problem, we had to sample them. So you can think of them as mini states. And I'm going to show them to you at various times because they have some nice properties that I can use. So here's these county groupings. These are counties clumped together. So here are 2 county groupings, and you see the same at the county level. This is Mecklenburg, where Charlotte is. You see the exact same kind of jump that we saw before in that huge jump, and the same kind of jump here in a more rural county, Columbus, Pender, Wilson. All right, so let me just kind of go on. So let me say, there's 2 kind of things when you have this. You can either propose better algorithms to lay on top of Metropolis-Hastings, or you can propose better proposals. So we're going to start off by proposing a better proposal. Actually, we're not going to. So the first one who did this was, actually some other people tried. People tried something like Swenson-Wong or Wolf algorithm, if you know what that is. It doesn't do as well. But Moon Duchin and her group, and Daryl Dufour, had the following idea. They said, look, these clusters, this is one of these county clusters, is really just a partition of this graph into 3 graphs. Let's just evolve those by doing the following. Let's pick two graphs, two precincts, 2 districts, I can't say anything right, 2 districts, merge them together, draw a new spanning tree on that one, and then using a breadth first search, sweep across this to find where I could cut it so that the population was well balanced. Then pick at random one of the edges that clip that well, and then I get a new district. So they call this recon, because it's like recombination, because somebody else was doing something kind of like this in genetic algorithms. Now that's really great, it does a great job. There's one problem with it. You don't know what the invariant measure is. There's some real problems. You might think you could figure it out. They tried for a while. There's some complications because of this step. You're not picking the unique one. You're picking over a clump of them, and it messes up all the things you think you know about nice spanning tree calculations. At least that I know. I'm hoping Jim will tell me otherwise. And then you say, well, that's not a problem. If I have a chain, you just told me how to fix that. If you have a proposal and you want to sample from a different distribution, just use Metropolis Hastings, Metropolize to fix it. The problem is that calculating the forward and backwards probabilities here is really hard. So we had a simple idea, which it kind of was intuition at the beginning because it fits into my brain under my general idea of kind of Bayesian data augmentation. Like, oh, if I can't calculate this efficiency, add some more degrees of freedom so I can calculate it efficiently, and then just forget to tell the people who are talking to me that I actually have these other degrees of freedom in my problem that I'm also simulating, right? That's what data augmentation is, right? Bayesian sampling. So let's do that. Instead of having partitions, let's just replace these with spanning trees. So now I have a spanning forest. And you're like, that's silly. How can that possibly make a difference? So in other words, instead of sampling this measure, so tau in this whole talk from now on will be the number of spanning trees on this partitions. So when you have a collection of partitions, it's number of spanning trees on this one, number of spanning trees on this one, number of spanning trees on this one. And so I put this gamma here because like beta, this will be another parameter that I can temper on. And so if I change from partitions to spanning trees, this is just the change in the measure. It's uniform over spanning trees. And so now we have the following thing. We're going to pick 2 districts to merge. We merge them, we draw a new spanning tree, we cut it, but now we return the spanning tree. Okay, that seems silly. That seems almost exactly what they were doing. It turns out that you can win if you do that. You can really save a lot of, yay math. You can actually do the inverse problem much better. I'll try to convince you of that, but let me first just say a little bit more about it. So here's the outline of that algorithm. So the hard part is commuting the forward probabilities and the backwards probabilities. And I want to convince you that we can do that effectively. Maybe I should say something about the algorithmic questions. So how do you do this if you don't know? You can, those of us who are alive in the 90s, mathematically know this for sure. So if you can calculate this, you can draw uniformly from spanning trees on a graph using Wilson's algorithm, which is a clever kind of self-loop erase random walk where you pick 2 nodes, you walk until you hit that other node, and if you ever double back on yourself, you erase the loop and keep what you have, and when you hit that other node, you freeze it.